Hi, in this video we'll be solving paper 2 variant 2 May-June 2024 AS level physics. Question 1a, the list below shows some SI quantities. Underline the quantity that's not an SI base quantity. So these quantities include mass, length, time, current and temperature. Charge here is not an SI base quantity. B, a square solar panel with sides of length 1300 millimeters. Right away we'll convert this to meter, which will be 1.3. So this panel is shown in figure 1.1. Light is incident normally on the solar panel. Incident normally meaning at right angles or at 90 degrees. The power of the light incident on the solar panel is 750 watts. Calculate the intensity of light. In the chapter of waves for our syllabus, we learned that intensity is equal to power divided by the area upon which light is incident, and also that intensity is proportional to amplitude squared. So power here is given as 750 watts. Area is the square area of square panel, which will be the side squared, and that would be 750 divided by 1.3 squared. This is equal to 440 watts per meter squared. 2. The percentage uncertainty in the incident power is 3%, and the uncertainty in the length of each side is plus or minus 5 millimeter. Calculate the percentage uncertainty in the intensity of light. To find the percentage uncertainty of intensity, you would add up the percentage uncertainty of power to the percentage uncertainty of area. We are already given with the percentage uncertainty of power, which is 3, and to find the percentage uncertainty of area, okay, let's just start with the fact that you are here given with the uncertainty of length and not area itself. So area will need to be considered in terms of length, which is length squared, and if you want to find the uncertainty of area using the uncertainty of length, you would multiply the power of length, so that's 2, with the uncertainty in length, and that is the value of uncertainty, that's 5, divided by the measured value. Okay, so this is 5 millimeter. Let's just convert that to meter. This will be 0.005, the uncertainty, divided by the measured value of length, which is 1.3 meter for the solar panel. So this will give you the uncertainty of area. To convert this into percentage uncertainty, you would just multiply that by 100. To the percentage uncertainty of power, which is 3, you will add 2 times 100 times the uncertainty of length, and this is a total of 3.769, which is rounded to 4%, plus or minus. Now be careful of these significant figures here. When we usually round our final answers to 2 significant figures, however, as you can see here, the question points out the percentage uncertainty in 1 significant figures only, so you'll need to follow the pattern already set in the question. The useful power output of solar panel is 160 watts. Calculate the percentage efficiency of solar panel. So percentage efficiency is 100 multiplied by useful power output divided by total power input. As the question mentions, the useful power output is 160, and as we read earlier, the power input is 750 watts, and that is equal to 21%. Power input is the power of the light which is incident on the solar panels, because this power will be providing the energy. 4. Another square solar panel is placed so that light of the same intensity is incident normally on it. The new panel has shorter sides than the original panel. The new panel has the same power output as the original panel. State and explain whether the efficiency of the new panel is greater than, less than, or the same as efficiency of original panel. Since we are going to be comparing the efficiency of the two panels, we will need to consider their ratios of power in by power out. So let's compare the older versus the new panels. In the older panel, the side length is longer, right? So that means okay, I got it. This should be power out or power in. Power out for both is the same, so let's just write it that way. Whereas power in depends on the surface area which is available to receive the energy or the power of the light incident on it. If the size of the older panels is larger, that means that larger surface area is able to receive more power. Therefore, the input power for the older one is going to be greater. So power input for older will be greater than the power input for the newer one. That means the efficiency fraction for the newer panel will be smaller. Since the denominator for newer is smaller value, this will lead to a larger fraction and therefore larger efficiency for the newer panel. To put this into numerical values, let's say power output for both of the panels is 160 watts. Now as for the older one, which has a larger surface area, if it has a surface area of 100, this would lead to an efficiency of 160%. Whereas if you were to reduce the size of the solar panel, therefore reducing the power input, this could be any number. I'm going to use 10 for just for the sake of simplifying it, and this would lead to a higher efficiency value. So there you have it. Question 2. A skydiver jumps from an aircraft at time 0 and then falls vertically downwards. The variation with t of her velocity is shown in figure 2.1. Because this skydiver is jumping through the sky and air resistance is not negligible, here you will need to use your knowledge of free fall. Under the force of gravity. Few things you need to note about a velocity time graph is that the area under the graph is equal to the displacement, and a constant line which has a gradient of 0, or the line which is parallel to x-axis, is the region where velocity is constant, whereas curves here will denote changing acceleration. Since the gradient is decreasing for this curve, as you can see the graph becoming less and less slanted and moving towards more of a horizontal position, that means the gradient is decreasing or acceleration is decreasing. Because remember, acceleration is change in velocity over change in time, which here is the gradient of this graph. A part 1, using figure 2.1, state the terminal velocity of the skydiver. What is terminal velocity? This is a velocity when the skydiver will fall at constant velocity because the forces acting on the skydiver in the vertical dimension would sum up to a value of 0. And according to Newton's second law, when there is no resultant force, there is no acceleration. So this will lead you to Newton's first law, where an object will fall with constant velocity or remain at rest unless acted upon by a resultant force. And the constant velocity is shown in this graph by this section of the graph, and this is equal to 39 meters per second. Part 2. By drawing a suitable line on figure 2.1, determine the acceleration of skydiver at time 9. So at this time of 9 seconds, the graph is a curved region, which means to find the gradient or the acceleration at this point, you will need to draw a tangent. This tangent should only touch the coordinate at which the value of x is, or time is 9 seconds. It should barely just touch that point. And another tip for making this tangent as accurate as possible is try to get these two angles to be as close to each other in size as possible. Now you will pick any two coordinates on this graph, and the further away they are from each other, the more accurate they will be. I'm going to pick this one over here, which is 15 seconds for 41 meters per second, and this one over here, which is 1 second for 27 meters per second. And using this, acceleration is equal to delta v, change in velocity over time, which is the gradient here, and that will be 41 minus 27 divided by 5 minus 1, and that is equal to 1 meters per second squared. Your values can range from 0.9 to 1.1 meters per second squared depending on the coordinates you have chosen. The mass of the skydiver and her equipment is 68 kg. The upthrust on the skydiver is negligible. So you have the skydiver. I'll just be using this shape for simplifying it. Simplify this. With 68 kg of mass acting downwards after reaching terminal velocity or constant velocity, which is 39 meters per second. The skydiver opens her parachute at time t1. A total drag force of 1800 Newton acts on the skydiver. Determine the magnitude and direction of acceleration of skydiver at time t1. So at time t1, a force of 1800 Newton of drag force acts upward. The reason it acts upwards is because drag force acts in a direction that's opposite to the direction of motion, which is for the skydiver falling downwards. So the drag force acts upwards, and let's just convert the mass as well into force. You will multiply that by 9.81. Determine the magnitude and direction of acceleration of the skydiver at time t1. This scenario of a skydiver falling through the sky, opening up a parachute, is a common one in our syllabus. So I would encourage you all to familiarize yourself with the concepts and all of the stages in this motion. After reaching the terminal velocity, when the parachute opens up, it will increase the surface area upon which the resistive force or the drag force is acting. And you need to remember this about drag force or resistive forces in general. When the speed of the object increases or when the surface area of the object increases, the opposing forces will increase, which is why in this case the skydiver initiates by falling at terminal velocity or constant speed, and then the parachute opens up. In other words, the surface area which is available for drag forces to act upon will increase, and this will increase the resistive forces opposing the motion of the skydiver, and this will eventually cause the skydiver to decelerate or slow down, meaning that the skydiver will now travel downwards with a decreasing speed. This means the direction of acceleration will be in opposite direction to the motion, because the diver is decelerating. Direction of acceleration will be upwards. And to find the value of acceleration, you will need to find the net force. Since we will be using net force is equal to mass into acceleration, and you are hinted to be using this formula through the value of skydiver given over here. And now let's focus, since we are considering acceleration in the vertical dimension, we will need to consider the net forces acting on the diver also in the vertical direction. In this case, the two forces acting on the diver are the drag force and the weight of the diver. They are acting in opposite direction. That means when you sum them up, one would be positive, one would be negative. Since we already know the acceleration is acting upwards, that means the upward acting force must be greater than the downward acting force, which is why I'll just take the drag force as positive and the weight as negative. You can do the opposite, that's alright as well. So you sum up these forces, which is 1800 minus 68 multiplied by 9.81 to find the net force, and divide that by the value of mass to find acceleration. Which is equal to 17 meters per second squared. Parachute is fully open at time 2. At a later time, t3, the skydiver reaches a constant velocity of 5.7 meters per second. Describe and explain the variation with time of the magnitude of her acceleration between time 2 and time 3. We know the parachute opening causes deceleration, that is, the speed of the skydiver will decrease. That means when the parachute is fully open at T2 and beginning from T2 until T3, the skydiver will decelerate, or the skydiver's velocity will decrease, and after T3 the diver will move at this constant velocity. Recall that deceleration of the diver was due to the drag force acting on the diver. Recall that the deceleration of the diver was due to the drag force acting on her, and drag force depends on the speed of the moving object. When the diver slows down between T2 and T3, the drag force acting on her will also reduce. This means the net force, and hence the deceleration of the diver, will also decrease until the point where the drag force acting on her and the weight become equivalent in their values. And at this point, she will have attained constant velocity and will have entered T3 when she begins to travel at this constant speed. Part 2. Calculate the change in momentum of skydiver between T1 and T3. Change in momentum is equal to mass multiplied by final velocity minus initial velocity, that is 68, multiplied by the final velocity at T3 is 5.7 and initial velocity at T1. Okay, T1 is when the skydiver opens her parachute at the first terminal velocity, which can be obtained from the graph, and that's 39 meters per second. This will lead you to 2300 Newton second. Correct to two significant figures. Question 3. Lightning occurs when a charge builds up in the atmosphere, creating a potential difference between the ground and the atmosphere. During a lightning strike, there is an average current of 3.3 times 10 raised to 4 ampere for a time of 2.6 times 10 raised to negative 5. Calculate the charge transferred during the lightning strike. So the charge transferred through the lightning strike is current multiplied by the time for the charge to pass, and that's very simple using the information given in the question, which is 0.86 coulombs. The potential difference between the ground and the atmosphere is 3.3 times 10 raised to 7 volts. Calculate the average power in gigawatts transferred during the lightning strike. 1 watt is equal to 10 raised to 9 gigawatts, so you'll convert your answer using this fact. Using the information we are given, we can use the formula power is equal to voltage multiplied by the current, and that's again very straightforward. This is equal to 9.9 times 10 raised to 11. You divide that by 10 raised to 9, and this will lead you to 990 gigawatts of power. C. A lightning rod is attached to a tall building to conduct charge safely to the ground. The lightning rod is modeled as a uniform cylindrical copper cable of length 95 meters that runs from the ground to the top of the building, as shown in figure 3.1. Part 1. The resistance of the rod is 9.6 ohms. The resistivity of copper is 1.7 times 10 raised to negative 8 ohm meter. Determine the radius of the lightning rod. We are giving with resistance, the resistivity, as well as the length of the rod, which is 95 meters, and this should remind you of the formula. Resistance is equal to resistivity multiplied by length divided by cross-sectional area for a conductor like copper itself, and cross-sectional area is equal to pi r square. That means radius is equal to resistivity length divided by pi and resistance, and you take the square root of all of that. This is equal to 2.3 times 10 raised to negative 4 meter of radius. Part 2. The radius of the copper lightning rod is doubled with no change to its length. So state the effect of this change on the resistance of the lightning rod. This is a 1 mark answer where you just need to look back at the formula we just used. Resistivity and pi are constant values, therefore resistance is directly proportional to length and it is inversely proportional to the radius squared. Since length remains constant, that means resistance will change with the radius, and when you multiply radius by 2 and square it, that means you are going to increase this denominator by a factor of 4, and if you increase the denominator, that means you are going to decrease the value of resistance by a factor of 4. A section of lightning rod of length 0.12 meter is removed for testing. A tensile stress of 1.9 times 10 raised to 6 Pascal is applied. Tensile stress is the stress applied, as you can see here, along the length of this lightning rod. And the formula of stress is equal to applied force divided by cross-sectional area, which is why it has the same units as pressure. The section of the rod obeys Hooke's law. That means it will follow the rule where force is equal to spring constant multiplied by the extension. The Young modulus of the copper is 1.3 times 10 raised to 11 Pascal. Young modulus is equal to stress over strain. Calculate the extension of the section. Alright, this is a 3-mark answer. Let's see where in all of these the information provided can we find the extension. Since we are not given with the spring constant, we will most likely not use this formula. However, we can use the Young modulus, since stress is equal to force divided by area and strain is equal to extension divided by original length. This can also be written in a fraction as force divided by area multiplied by extension divided by length. Right, and we are supposed to find the extension. Now the tensile stress or force divided by area is already given as 1.9 times 10 raised to 6. The original length is 0.12 meters, and Young modulus is also given as 1.3 times 10 raised to 11. That means extension is equal to Young modulus multiplied by the length and divide that by stress, which is equal to 1.8 times 10 raised to negative 6 meter of extension. Question 4. A pinball machine uses a spring to launch a small metal ball of mass 4.5 times 10 raised to negative 2 kg up a ramp. The spring is compressed by 8.8 times 10 raised to negative 2 meter and held in equilibrium as shown in figure 4.1. The ramp is at an angle of 15 degrees to the horizontal. The spring obeys Hooke's law. That means once again it will follow force is equal to spring constant multiplied by extension, and it has a spring constant of 29 Newton per meter. Calculate the elastic potential energy in the compressed spring. The formula for elastic potential energy states is 1/2 multiplied by the spring constant multiplied by the extension squared. So that will be 29/2 multiplied by square of the extension of the spring. Here it's compressed. Both of these values can be used for calculation purpose, and that is equal to 9.3 times 10 raised to negative 2 joules. This is the energy, elastic potential energy, that's stored in the compressed spring. The spring is released and expands quickly back to its original length. So when the spring is released, it will lose the elastic potential energy that was originally stored in it. 1. Calculate the increase in gravitational potential energy of the ball when the spring returns to its original length. The change in gravitational potential energy of the ball will be due to the height that it gains or due to the vertical distance that it travels when it moves through this distance of 8 times 10 raised to negative 2 meters. So you are given with the slanted distance as well as the angle of this distance from the horizontal. To find the change in gravitational potential energy, you need to know the change in height. How do you find the change in height when you are given the slanted distance at an angle from the horizontal? You consider the right angle triangle and use trigonometry to find the opposite side to the angle, as well as using the hypotenuse side in this right angle triangle. Sine theta is equal to opposite over hypotenuse. That means the opposite side, which is the height over here, will be equal to sine 15 multiplied by 8 times 10 raised to negative 2. This will be the change in height, or the height gained, the distance traveled, the vertical distance traveled by the ball. So the change in gravitational potential energy is equal to mass multiplied by gravitational constant multiplied by the change in height, which is equal to the mass given in the question earlier, the constant value, as well as the change in height. And this will lead you to the final answer as 9.1 times 10 raised to negative 3 joules of energy. The ball leaves the spring. Okay, let me just, we had the spring compressed and the ball will travel through this distance. The ball leaves the spring when the spring reaches its original length. Assume that all the elastic potential energy of the spring is transferred to the ball. Okay, so we just found that the ball gains gravitational potential energy. Now we are finding out the elastic potential energy initially stored in the spring is now also gained by the ball. Calculate the speed of the ball as it leaves the spring. To answer this question, you will need to recall the law of conservation of energy, which states that energy can neither be created nor destroyed. That means total energy at the initial position must be equal to the total energy at final position. And here, since we need to find the speed of the ball, we'll need to consider the energy value, some of the energies possessed by the ball at the initial and final positions. Initially, there's only the 9.3 times 10 raised to negative 2 joules of elastic potential energy stored in the spring, right? And finally, when the spring reaches its original length, or when the ball has moved, some of the elastic potential energy is converted to the gravitational potential energy of the ball, and the remaining portion of the elastic potential energy of the spring is converted to kinetic energy of the ball. This will be converted to gravitational potential energy plus the kinetic energy of the ball. We say kinetic energy because the ball will move, and energy of motion is due to kinetic energy. Now we just need to put this information into equation. So elastic potential energy initially stored in the spring is equal to the sum of gravitational potential energy plus kinetic energy gained by the ball, where kinetic energy is equal to half mv squared. So this elastic potential energy is 9.3 times 10 raised to negative 2 joules is equal to 9.1 times 10 raised to negative 3, which we just found in our previous answer. This means the speed is equal to 9.3 times 10 raised to negative 2 minus 9.1 times 10 raised to negative 3 divided by or multiplied by 2 divided by 4.5 times 10 raised to negative 2, and you take the square root of this fraction to find your final answer, and that will be 1.9 meters per second. Let's just put this in brackets. See, the ball comes to rest on horizontal trapdoor of negligible mass at a distance d from its pivot. A force Fx vertically downwards at a distance of 2 cm from the pivot. Let's just convert this to meters right away. The trapdoor is in equilibrium when F is 1.7 Newton. Calculate D. Since we are dealing with equilibrium, it will help to recall the conditions of equilibrium. So the two conditions for equilibrium that must be met are: number one, the sum of upwards forces acting on an object must be equal to the sum of forces, the downward forces, sum of downward forces. And also the sum of clockwise movement must be equal to the sum of anti-clockwise movement. Since we are dealing with distance here, where movement is equal to force multiplied by distance, we'll be looking at the equation of, we'll be considering the moments caused by the two weights or the two forces here, which are this one, 1.7 Newton, that will cause anti-clockwise moment, and the weight of the ball, the force from ball, which will cause clockwise moment. So anti-clockwise moment must be equal to clockwise moment. That means force into distance, that is 1.7 multiplied by 0.02, must be equal to the force due to the ball, which is its weight, that is mass multiplied by gravitational constant, multiplied by the distance from the pivot, that is unknown. So distance is equal to 7.7 times 10 raised to negative 2. Part 2. Force F is decreased from 1.7 Newton. State the direction of resultant moment about the pivot on the trapdoor. When the force F is decreased from 1.7 Newton, the moment caused due to this, or the anti-clockwise movement, will decrease, equilibrium will be disturbed, and this will cause the trapdoor to tip downwards due to from the weight of the ball in the direction of clockwise movement. So the resultant moment will be in clockwise direction. (5a) State Kirchhoff's second law. According to this law, the sum of EMFs the sum of electromotive forces are equal to the sum of potential differences around a closed loop, and this results from law of conservation of energy. A battery of electromotive force 9 volt and negligible internal resistance is connected in series with a variable resistor X and thermistor Y as shown in figure 5.1. So here's your variable resistor and the thermistor. For variable resistor, the value of resistance changes, and thermistor is a semiconductor where the resistance of this electrical component depends on the temperature. It varies inversely with temperature, which you can see by the relationship between temperature and resistance for the thermistor. As temperature increases, the value of resistance in the thermistor will decrease. Part 1. The current in circuit is 1.1 times 10 raised to negative 2 ampere. The potential difference across Y or the thermistor is 4 volt. Calculate the resistance of X. The value of current here is the value of current in the series circuit, where current in all these electrical components is the same. So that means the current through both Y and X is the same. We already know that about X now. As for the voltage, as we just saw according to Kirchhoff's second law, the sum of EMF is equal to the sum of potential difference in a closed loop. What that means in the context of a series circuit is that the 9 volt of potential difference will be divided between the electrical components in this circuit. If 4 volt of potential difference is applied across Y, that means the potential difference across X must be 5 volt. Using this, we can find the value of resistance, which is equal to potential difference divided by the current, and that's 450 ohms. The temperature of Y, or the thermistor, is changed to 190 degrees Celsius. The resistance of X remains unchanged. So this will be 450 ohms. And using this temperature, we can find the resistance for thermistor. Determine the new potential difference across Y. Okay. Let's see, at 190 degrees Celsius, the resistance of Y is 25 ohms. Let me just redraw the circuit. We have 9 volts of EMF available to X, which has 450 ohms of resistance, as well as Y, which has 25 ohms of resistance at 190 degrees Celsius. Previously, we knew that the current through thermistor was the values of current and the potential difference through Y. That means the resistance of thermistor earlier was 360 ohms, and now it has reduced to 25 ohms. Since we know from Ohm's law that voltage is proportional to resistance, that means if the resistance value of the thermistor decreases, the potential difference across the thermistor must also decrease. So clearly the proportion of potential difference across X and Y in this new setting will change. And to find the exact values of potential difference across X and Y, we'll need to know the current through the circuit. Since this is a series circuit, that means the current through each electrical component will be the same, where current is equal to total potential difference divided by the resistance of the series circuit. That is 9 volt divided by the sum of all electrical components in this circuit, and that is equal to 0.0189 ampere. So this current will be passing through both of these electrical components, and now we know the values of the resistance as well as the current. Therefore, the potential difference across Y is equal to 0.0189 multiplied by its value of resistance, that is 0.47 volt. Part 3, the resistance of X is increased. So now the value of resistance of the variable resistor is increased and the temperature of Y remains at 190 degrees. So that means this value over here will remain the same, whereas the resistance of X will increase. It will be greater than, the new resistance will be greater than 450 ohms. That means a higher proportion of 9 volt will be available to 450 ohms now. That means the potential difference across 450 ohms, that means the potential difference across variable resistor will increase and potential difference across thermistor will decrease. By reference to the current in the circuit, state and explain the effect of this change, if any, on the potential difference across Y. This here is Y. Now we need to give our answer in terms of current. Once again, to answer this question, we will rely on Ohm's law. When the resistance of any component in a series circuit increases, the total resistance of the series circuit will increase, which is contrary to total resistance in parallel. Keep that in mind. As the total resistance of the circuit will increase, the current will decrease, current in the circuit will decrease. And we know the relation between resistance and current from Ohm's law is that they are inversely proportional. So resistance of circuit increases, the current decreases. Since V is equal to IR and R, or the resistance value of Y, remains constant, whereas the value of current decreases, that means the potential difference across Y will decrease. And that's how you can use the Ohm's law to give your answer in terms of or with reference to current. Question 6. Light of a single frequency is incident normally on a diffraction grating. An interference pattern of bright and dark fringes forms on semicircular screen shown in figure 6.1. Here you will need to recall the concept of interference, where bright and dark fringes are formed from constructive and destructive interference. When two waves overlap in phase, they will result in constructive interference, meaning that the amplitude or the energy or intensity will be increased. It will add up. This will result in bright fringes, whereas for dark fringes, it results from destructive interference, where waves will overlap out of phase, where the energies will cancel out when they sum up. So let's say if this was plus 2, here this is minus 2, they will add up to an amplitude or energy of 0, resulting in dark fringes. And this pattern will be formed all across the screen, where you will have a central bright fringe surrounded by a series of bright and dark fringes. And these fringes are given numbers. So the central fringe has an order of maxima 0, and this will be the first one, and as you go away further away, they will be numbered accordingly, and they are numbered separately on either sides of the central fringe. So this is again bright fringe, and alternately these areas will be the dark fringes. And similarly, you'll have the same pattern on the opposite side as well. The light has a wavelength of 520 nanometer. Separation of the slits of the lines in the grating is 3.8 times 10⁻⁻⁶. Determine the total number of bright fringes formed on the screen. It will help to recall the formula of diffraction grating, which is d sine theta is equal to n lambda, where wavelength is given as 520 nanometers. N is the number of maxima, or the total number of bright fringes in this case. N is the order of maxima, which we need to find out. D is the separation given in the question, and for the total number of bright fringes, we will assume that theta is equal to 90 degrees. And that's because theta is the angle between the central fringe and the order of any particular maxima. So any particular fringe, let's say if this here is the theta. The theta, when you want to find out the maximum number or the total number of bright fringes, you will consider that the last fringe that forms on the screen will be, let's say, this one over here. So you'll have a fringe over here, and as you can see, the angle between this fringe over here and the central fringe is 90 degrees, which is why theta for the the maximum number of fringes is considered as 90 degrees. So order of maxima is equal to 3.8 times 10 raised to negative 6 multiplied by sine 90 divided by the wavelength, which is equal to 7.3. Now this will give you the number of bright fringes on one side of the central fringe. To find the total number of bright fringes formed on the screen, you will need to consider both the bright fringes on one side, on this side, as well as the number of fringes on the other side, which the number of fringes will be the same. Since you have just found half of the number, you will multiply that by 2. So 7.3 multiplied by 2 will be equal to 14.6, and that can be rounded off to 15 fringes. B. The light is replaced with a red light of a single frequency. State whether the frequency of red light is greater than, less than, or the same as the frequency of original light. Frequency is inversely proportional to the wavelength. Because red light has a longer wavelength between 620 to 750 nanometer compared to white light, which has a range of 400 to 700 nanometer, the shortest wavelength in this range of white light is smaller than compared to the smallest wavelength of red light, meaning that red light will have a longer wavelength, and so it will have a smaller frequency. State and explain the effect of this change on the number of bright fringes formed on the screen. A calculation is not required. Again, we'll recall the formula: d sine theta is equal to n lambda, where the number of fringes on the screen is equal to d sine theta divided by lambda. So that means the number of fringes is inversely proportional to wavelength, and it's directly proportional to the frequency. If the frequency of red light is smaller, that means the number of fringes must also be smaller. Question 7. A particle Q and a particle R are each composed of one quark and one antiquark. So particle Q has quark as well as an antiquark, and R has the same. State the name of the class or group of particles that includes Q and R. Quarks. First off, quarks are fundamental particles that carry positive or negative that can carry charges, positive or negative, and their antiquarks carry the opposite charge. So for example, if an up quark has a charge of plus 2/3 of an elementary charge, that means the anti-up quark will have negative 2/3 of an elementary charge. As for the class of particles that includes Q and R, any particles that are made up of one quark and one antiquark are known as mesons. Q has a charge of -1 elementary charge and R has a charge of 0. Complete table 7.1 to show a possible second quark in each of Q and R. I think R is easier, so I'll just start with that. R has a charge of 0. That means the charges of both of these particles must add up, must be equal and opposite to each other to lead up to 0. Anti-up charge. So up charge is has a negative two-thirds of an has a positive two-thirds of an elementary charge. So the anti-particle, the anti-quark or anti-up charge, will have negative two-thirds of an elementary charge. To cancel this out, you will need a positive two-thirds of an elementary charge, which can be carried out by an up quark, a charm, or a top quark. Now let's look at Q, which has a charge of -1 elementary charge. The quark in this is strange, as for the second quark, which must be an anti-quark since strange is a quark, so second charge must be an anti-quark, and it needs to add up to strange such that their sum is equal to -1. What is the charge of a strange quark? That is -1/3 of an elementary charge. To that, when you add the unknown anti-quark, their sum must be equal to -1 of an elementary charge. This means X must be equal to -2/3 of an elementary charge. The quarks that carry negative charges are all -1/3 of elementary charge, that are down, strange, and bottom quarks all have -1/3 of charge. So this anti-quark is an anti-quark of an originally positive quark, like up, top, or charm. That means this can be anti-up or anti-charm or anti-top. I'll go with anti-up quark. And this is it. We are done with this paper. Thank you for watching.